units. Units are very important. Here's an example, not typical, but a great example. In 1999, NASA lost the $125 million Mars Climate Orbiter. The reason, when they were trying to adjust the orbit, one group was doing their calculation in inches, and one was doing the calculation in centimeters. They did not communicate that clearly to each other, and as a result, the thing was programmed incorrectly, and it got too close to Mars, got pulled in and crashed. $125 million gone over inches versus centimeters. Now, thankfully, none of the mistakes you make with units this semester will have ramifications like that, right? But units are really, really important, okay? So we're going to learn about units and how they work, and we're going to practice converting units from one thing into another. And what I want you to get into the habit of doing is including your units, because units are important. If you go to McDonald's and you say, I want 2, what are they going to give you? They're going to say, well, did you want meal number 2? No, I wanted 2 ice cream cones. Well, how are they supposed to know that? Right? You have to tell them 2 of what? And that's the way it is with units. You know, this thing is 5. It's 5 grams. It's 5 meters long. It took 5 minutes to make. We don't know what you're talking about. So units are really, really important. A unit is just a standard quantity used to specify a measurement. And if you stop to think about it, all units at some point were just made up. They were just made up, right? There's no naturally occurring unit, right? A foot. Do you know where that came from? It was the length of the king's foot. Get a different king who has bigger feet. Now your unit changes. A little awkward. They figured that they had to do something about that pretty quickly. But there are different systems of units. The 2 most common are the metric system, which most of the world uses, and then the English system, also sometimes called the imperial system, which is what we use in the United States because we're stubborn, I guess. We spent all that time and energy breaking free from the English, and then we kept their system of measurement. They don't even use it anymore. What is up with that? I really don't know.
It's like modern taking it back, basically.
Yeah, it's like we're just like, I don't know. Anyway, the metric system to most Americans is kind of mysterious and strange. You know, you go up into Canada and the speed limit signs are kilometers per hour, and you're like, I just don't have a feel for what that means, right? Because we're used to miles per hour. But when you learn how the metric system works, it's much easier to make sense of, because everything is just factors of 10. You don't have these weird conversions like there's 12 inches in a foot and there's 3 feet in a yard and there's 5,280 feet in a mile. Where did all these numbers come from? Right? They came from people making up a unit and then comparing it to this other made-up unit, and it's like, well, that's an awkward number, but there it is, 5,280. In the metric system, all the units are related to each other by factors of 10. So it's 10 times bigger or 100 times smaller, and they use prefixes. The prefixes are the same throughout the whole metric system, so you'll learn a set of prefixes, and you can use them for everything. There's no trying to remember how many gallons are in how many quarts are in a gallon, how many tablespoons in a cup. You know, those are things that are really hard to remember because all of them are different. So the metric system is much, much better, and I hope to convince you of that. Technically, scientists use the International System of Units, or the SI system. it is based on the metric system, and in my opinion, the differences between the SI system and the metric system are just really not even worth talking about. So I consider them to be basically interchangeable, although they are not technically exactly the same. So these are the base units in the SI system. And one of the differences is in the metric system, some of the base units aren't exactly the same. So for mass, in the SI system, the base unit is kilogram. In the metric system, it's gram. Really, that's the only difference I can think of. Ooh, that's really big, right? So these first quantities, length, mass, time, temperature, and amount of substance, we will encounter in Chem 1A. Electric current and luminous intensity, you can just skip those. We won't get into those at all. But these are units, and these are their symbols. Most units are going to have a one-letter abbreviation. So meter is a lowercase m. Kilogram has two letters because it's got the metric prefix kilo in front of the unit gram. Second is the same second you're familiar with. K is the capital K for Kelvin, and we'll talk about that in a minute. Amount of substance is measured in moles. We'll talk about that later. The symbol for mole is MOL. Personally, I think MOL should be an abbreviation for molecule because it's a much longer word. I don't know why just knocking the E off of mole is really that significant, but they didn't ask me. So mole, MOL, is the abbreviation. We should have a rough idea of how big these units are. Meter is used to measure length. It's very similar in size to a yard. So this is a meter stick. It's not a yardstick, it's a meter stick because it's a meter long, 100 centimeters. It does have inches on it. If it was a yardstick, it would stop right here at 36 inches. So that's the difference between a yard and a meter. Really, really similar. If you're doing a calculation and you come up with, this basketball player is 6 meters tall, is that a reasonable answer? That'd be like 6 yards tall. That'd be 18 feet tall. That's a bit extreme, right? That's not going to happen. Nobody's that tall. So if we have an idea of how big these units are, it can help us identify if our answers are reasonable or not. Mass measures the quantity of matter. It is very similar in many ways to weight. Okay? But weight is measuring gravitational pull on an object. And gravitational pull is going to change, say, if you go to the moon. It actually can change a little bit in different places on the Earth because the gravitational pull is not perfectly uniform. We're going to just ignore that. So as long as we all just stay on this planet, we can kind of use the terms mass and weight interchangeably. But just keep in the back of your head, they don't really mean the same thing. The unit of mass is a gram or a kilogram. So the kilogram, we stay on the planet, mass, weight, roughly the same. How big is a kilogram? Well, a kilogram is pretty close to 2.2 pounds. So, your weight in pounds, divide that by 2, and that's your approximate weight in kilograms. The gram is what we use more commonly in chemistry because it's much smaller. 2.2 pounds is a lot of stuff. And so, if we were doing experiments with kilograms of compounds, we'd need giant beakers and we'd be wasting a lot of stuff. So we tend to use smaller amounts. And so the gram is a smaller unit, which is more useful. To have an idea of how big a gram is, we can remember that a nickel, which is 5 cents, has a mass of about 5 grams. So, well, is a gram a big unit or a small unit? Well, a nickel weighs 5 grams. That's pretty small, right? Unit of time is the second. This used to be defined in terms of days and years, except that, with the leap year and everything is kind of funky. And so now it's defined as the period of time it takes for 9,192,631,770 periods of the radiation emitted from a certain transition in a cesium-133 atom. That's a pretty precise definition, right? I just told you that because it's fun to say that long number. But the second in science is the same as the second we use in everyday life. Temperature. We're going to run into 3 different temperature scales. But the SI unit of temperature is the Kelvin. This is not a degree Kelvin, it's just Kelvin, right? And the symbol for it is a capital K. So temperature measures the average kinetic energy of the particles of a substance. And temperature also will determine the direction of thermal energy transfer. So if you have a hot object and a cold object next to each other, so maybe you put a cup of coffee into a cooler of ice. Is heat going to flow from the coffee to the ice or from the ice to the coffee?
From the coffee to the ice.
It's going to go from the coffee to the ice. The coffee's going to get colder, the ice is going to get warmer, and it's going to keep doing it until they're both at the same temperature. It never goes the opposite, where the coffee gets hotter and the ice gets colder. The temperature difference determines which way the heat is going to flow. Thermal energy transfer always goes from hot to cold. So the other scales are Fahrenheit and Celsius. The Fahrenheit scale is what we use in the US. They say it's going to be, 170 million degrees, maybe 107 degrees. They mean Fahrenheit, degrees Fahrenheit. The Fahrenheit scale has the boiling point of water at 212 and the freezing point at 32. Again, typical of English system, kind of random seeming numbers. There's a history and a reason behind that, but we could read about that on our own if we care. So the difference here is 180 degrees. The Celsius system, which is a metric unit because it's based on powers of 10, has water freezing at 0 and water boiling at 100 degrees. And those are actually the calibration points for the scale. And so you could make your own thermometer by having a glass tube with a liquid that is going to rise up. You could use mercury, or this is colored alcohol. And so you put your thermometer, it doesn't have any markings on it because you're making it yourself, right? You put your thermometer in some ice water, and the liquid comes down and settles at a point. And so you make a mark there, and you say, okay, that's 0. And you take the thermometer and you put it in a pot of boiling water, and it shoots up, and it stops, and water boils. Okay, that's going to be 100. And then you would just take that difference and divide it into 10 places, 100 places, and you'd have 100 degrees. And that's how they made the Celsius scale. So there's 100 degrees here and 180 degrees there. So they're not the same size, and 0 is not in the same place. So that makes converting units between Fahrenheit and Celsius a lot messier than doing like centimeters and inches or something, because 0 is not the same. Both of these scales allow for negative temperatures. So you can have negative temperatures on both of these scales. And then we have the Kelvin scale, also called the absolute scale. In the Kelvin scale, there are no negative temperatures. And this is done by assigning 0 Kelvin, which looks a lot like okay, but it's a skinny O, is 0K. That's absolute zero, which is the place at which molecular motion stops, or virtually stops. So the solid state of students, if you all sat perfectly still, held your breath, didn't blink and do anything, that would be like absolute zero. You can't get less motion than no motion, right? Temperature is a measure of the motion of the particles. So you get down to no motion, can't get any colder than that. There are still 100 units between boiling and freezing, and so the size of the Celsius degree and the Kelvin unit are the same. What's different is where is zero. So to convert between these temperatures, we're going to use these equations. So to find Celsius, if you're given Fahrenheit, you subtract 32, and then take that quantity and divide by 1.8. To find Kelvin, you take the Celsius temperature and you add 273.15. So let's do an example of that. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on A, the Celsius scale, and B, the Kelvin scale? So this is what they're giving us here, right? 85.6 degrees Fahrenheit. We're supposed to convert that to Celsius. So there's an equation for that. So we go find the equation. The equation says the Celsius temperature is equal to the Fahrenheit temperature minus 32 divided by 1.8. So we'll just plug our Fahrenheit temperature in here. You should be bringing your calculator to class, and when we do problems like this, pull it out and make sure that you're communicating properly with your calculator. Because there's nothing like doing it. And sometimes you'll find that your calculator is giving you the wrong answer. It's your calculator's fault, it's not your fault. But I'll come over and I'll be stern with your calculator and shape it up for you, okay? So if you're having trouble with your calculator, just let me know. So here we have 85.6 minus 32, and that's in parentheses. The subtraction needs to be finished before we divide by the 1.8. So if you use parentheses, your calculator will understand what you mean. If your calculator doesn't have parentheses or you don't like using them, what you can do is you can do 85.6 minus 32. And to force your calculator to finish that, because it knows PEMDAS and it knows that we should do the dividing before we do the subtracting, and it'll get confused. So I'm going to press enter. That makes it finish the subtracting. It's showing me 53.6. And then I divide by 1.8. And then I'm going to write down everything my calculator says. I'm not sure if that's the right number of sevens, but you get the idea. Right? A whole bunch of sevens. And so this would be in degrees Celsius. So we learned about significant figures, right? This is one of those messy situations where you've got the two different rules going on. And so using sig figs to find the uncertain digit in here is going to involve some thinking, and it's not really necessary. There are lots of times when we need to think about something, but whenever possible, I like to find a way where I don't have to think about it. I can just, it's like, oh, this is what we do. We don't have to think about it. So with temperatures, not with other things, but with temperatures, what I'd like you to do is just look at where was the last decimal place in the original number. So this one ended in the first decimal place. So that means I want to round my converted temperature to the first decimal place. So the rounded value would be 29.8 degrees Celsius. And if you're curious why we can do that, I'll be happy to talk to you about that during lab. So any questions about the calculation? Anybody need me to yell at their calculator? We're also supposed to convert this into Kelvin. We did not give you an equation relating Kelvin and Fahrenheit. You could come up with one, but we don't need to use it very often. And so what we usually do is, if we have Fahrenheit and we need Kelvin, we'll just convert it to Celsius and then convert the Celsius to Kelvin. So the equation for Celsius to Kelvin, Kelvin equals the Celsius temperature plus 273.15. So it's better to use the unrounded number when we're continuing and doing more calculations. Do you have to type in all of those guys? No, you don't. My kind of rule of thumb, because I don't like copying down lots of random numbers, is here's your underlined digit, that's the last significant figure. Just keep 2 extra ones. Keep 2 extra ones. You don't even need to worry about rounding up or anything. Just keep the 2 extras. So I'm going to take 29.778 and I'm going to add 273.15. You can round up if you want, but you don't have to. And then my calculator shows me 302.92, and again it does the whole 7/7 business. So our original number had 1 decimal place. So this Kelvin value, I also want to have 1 decimal place. So 302.9 Kelvin. Any questions? So there are some questions like this on the worksheet of practicing different temperature conversions. So there, the answers pop up and got them right. Good. We need units of different sizes to measure objects or quantities of different sizes. So I live in Reedley, which is about 30 miles from Fresno City College. I wouldn't tell you that distance in inches. Could I? Yeah, we could figure it out. It's going to be a really, really big number. And, you know, it's like, well, how far is 500,000 inches? I don't know. We don't measure big distances in inches. We measure them in a unit that's closer to what we're measuring. So in the English system, we have all these weird relationships, speaking like inches and feet and miles, and then there's things like furlongs and all these other weird measurements of length. In the metric system, we've got the meter, and if we need it to be bigger or smaller, we just put a metric prefix in front of it. Those prefixes just multiply the unit by a factor of 10, making it either bigger or smaller. So an example here is the kilometer or kilometer. This prefix kilo means 10 to the 3. So 1 kilometer is 10 to the 3 meters. 10 to the 3 can also be written as 1,000. So kilo and 10 to the 3 are just different ways of saying the same thing. This is sort of like a nickname, a short name for 10 to the 3. These are some of the metric prefixes. Some of them are more important than others. So for this class, kilo, 10 to the 3, centi, 10 to the minus 2, and milli, 10 to the minus 3. if you don't have the energy or time or whatever to memorize all of the prefixes that are on the memorization list, which is not all of these, we are not going to use exa or peta or atto in this class. You can learn them if you want to, but we're not going to use them in this class. But if you don't have time to learn all the ones that I did tell you to memorize, at least learn these three, because these are going to show up a lot. The next most common ones would be micro, mega, and nano. But again, those three green ones, those are the really important ones. And they show the multiplier here in decimal notation. I don't even look at that. These are all 10 to the something. And aside from these two in the middle, all of the exponents are multiples of 3. So 10 to the third, 10 to the sixth, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. And then there's just these two weirdos in the middle, centi and deci. So how long is 4.5 megameters in meters? And so if we don't have those memorized, we go back to the table and we look, okay, which one's the capital M? Notice there's a capital M and a lowercase m and also a Greek m, because there are three prefixes that start with M. There's mega, which I think just from its use in everyday life, I think everyone understands that mega means big, right? Ooh, he's making mega bucks, right? Mega literally means a million. Mega is big. Milli is small. It's a small m. And then micro is even smaller. We ran out of English m's, so we used the Greek m, micro. So mega means 10 to the 6. So if we're wanting to know how long this is in meters, what we can do is write this, but instead of putting the prefix capital M, we put what it stands for.
So it becomes like a sig bit or a scientific
A scientific notation, yeah. So 4.5, now instead of capital M, I'm going to write times 10 to the 6 meters. Because this is what the capital M stands for. On the table, it shows 10 to the 6. I like to think of it as times 10 to the 6. So 4.5 megameters is the same as 4.5 times 10 to the 6 meters. And we can do that the other way as well. 7.13 times 10 to the minus 9 liters is equivalent to how many nanoliters? Well, the prefix nano is a little bit like the word 9, right? Nano, nino, 9. 9, 10 to the minus 9 is the prefix nano. So this part here can be represented by a lowercase n. So we could write this as 7.13 nanoliters. So this is just shorter, right, than times 10 to the minus 9. Questions 2 and 3 on the worksheet are going to have you do things like this. One of them is going to give you the unit with a prefix and ask you to write it without the prefix. And you just look up what the prefix means and you put in times that. And it'll end up in scientific notation. The other one will give you a measurement in scientific notation, and ask you to do it without the scientific notation. You just look up this factor of 10, it will match one of the prefixes, and you write the prefix in there. And this is to just help us to understand how the metric system works. So those are base units, and then there are derived units. Derived units are combinations of the other units. So speed in miles per hour, or a unit of volume like meters cubed. That's combining meters, meters, and meters. Meters times meters times meters. So yes, this is a picture of me, I am sitting in a cubic meter in a science museum in Oslo. I had a chance to go on a really fun trip, and it's like, well, at least get one slide out of this I can use in class, right? So I was working, right? Yeah. So that's how big a cubic meter is. Pretty big. You wouldn't want to live in there, but, pretty comfortable to just sit and hang out for a while. We measure volume. The volume of a cube is the length times the width times the height, right? We take the 3 dimensions and we multiply them. So if each side is 1 meter, 1 meter times 1 meter times 1 meter is 1 meter cubed or 1 cubic meter. We can do that with other units like millimeters or centimeters. Centimeters cubed is a unit of volume. Other units of volume that we use are liters and milliliters. And these are like gallons or ounces or cups or pints or quarts in the English system. Those are usually used for liquids, right? Liter and milliliter are typically used for liquids. Things like cubic meters, cubic centimeters are typically used for solids. So this big cube here is 10 centimeters on a side. So if we have little 1 centimeter cubes, it's going to be 10 cubes across and 10 cubes high and 10 cubes deep. 10 times 10 times 10 would be 10 cubed, right? So the volume of that big cube is 10 centimeters cubed, which would be 10 cubed meters cubed. So 10 cubed is 1,000. So 1,000 cubic meters. If you counted all those little cubes, there's 1,000 of them in there. This is a really useful table from your textbook. I would recommend, going to the slides, pulling this up on your phone, and taking a screenshot of it. Or if you don't care how pretty things are, just take a picture of it in your textbook. This is a really useful table of unit equivalents. The yellow cards, need to restock those. Those are all gone. But these yellow cards have a lot of units on them. Students love this page. It's got way too much stuff on it. You don't need all of those. Then you have to look through them all and find them. Most of the problems that we're going to do, you just need these in table 1.3. When you're doing unit conversions, we're going to learn how to convert units, and learning the process is what is important, not getting the answer, because I already know what the answer is. That's not why I'm asking you to do it. I want you to learn a process called dimensional analysis. And I want you to learn that because I know from experience that it will be helpful to you later in the class. I know that you could do a lot of these unit conversions really quick on your phone. Google will convert almost anything for you, right? But when you get to converting grams of hydrogen to grams of oxygen for a particular chemical reaction, Google's not going to help you. And Google will not help you on an exam because you're not going to have your cell phone. You need to do it yourself. So please do not use Google to do these problems for you. Now, if you want to use it to check your answer, that's fine, but learn how to do them yourself. The one thing that's not listed in this table that I think is really important is 1 cubic centimeter is the same thing as a milliliter. They're 2 different names for the same thing, right? And a cubic centimeter is what the medical profession calls a cc. cc for cubic centimeter. It's just a milliliter. Density is also using derived units. The density is the ratio of its mass to its volume. So density is the mass divided by the volume, or with variables d equals m over v. So we end up with units of mass over volume, so we can have things like grams per milliliter, grams per cubic centimeter. Density is a physical property that depends on temperature. Hint, hint, there's a question in the worksheet about this. So I'm going to tell you the answer right now. So if density depends on temperature, that means that one of these things changes with temperature. Is it the mass, the quantity of matter, or is it the volume? It's the volume. The quantity of matter can't change with temperature. How many particles you have is how many particles you have. Temperature is not going to change that. But temperature can change how much space it takes up. Some things change a lot in volume with temperature. Other things don't change very much. But sometimes even a tiny change is important. Have you ever stuck a can of soda in the freezer because you wanted to cool it down, and then you didn't set a timer on your phone, and you lost track of time, and you come in the next day, and what happened? It exploded in the freezer, and your mom's not real happy because it made a mess. Why does a can of soda explode? Because when the liquid, which is mostly water, freezes, its volume changes. It expands. And it expands enough that it's going to burst the can open. It'll happen with like water bottles and Gatorade and stuff too. If you want to freeze stuff like that, you need to leave some space at the top so that it can expand up instead of just all expanding out and breaking your container. So volume will change with temperature, therefore density changes with temperature. So this is a table, density of some common substances, and it specifies the temperature because at a different temperature, the density will not be exactly the same. It doesn't change a lot. So 20 degrees is cooler than what we are right now. We're at 25.3 degrees. It's a little warm for my taste, but it is what it is. 25 is pretty close to 20. Unless you're doing super, super precise things, close enough. There are two different densities listed here for ice, and they are given at different temperatures. At 0 degrees Celsius, ice has a density of 0.917. Water at 4 degrees Celsius as a liquid, just a tiny bit warmer, has a density of 1. You should not memorize these densities. If you need the density, you go look it up. On an exam, it'll be provided to you in one way or another. On the homework, Mastering Chemistry, they'll give you problems. They won't tell you the density. They won't tell you to look it up. I can't do this problem. I don't know what the density is. Go look at table 1.4. It's there. You just have to go look it up. The one thing that can be useful to remember is the density of water, 1 gram per cubic centimeter or 1 gram per milliliter. It's exactly that at 4 degrees Celsius. It's really close to that at higher temperatures. So sometimes you need to use that as kind of an estimate in a problem, but the rest of these you don't look up at all. Talked about chemical and physical properties. We can also describe properties as being intensive or extensive. So an intensive property doesn't depend on how much of the substance you have. So you've got a block of ice, and you're going to determine its melting point. It's going to melt at 0 degrees Celsius. It doesn't matter if you have a little tiny ice cube or if you have an iceberg. It's still going to melt at 0 degrees Celsius. It doesn't depend on how much stuff there is. The density of an object doesn't depend on how big it is, because it's the mass divided by the volume. Bigger objects are going to have a bigger mass, also a bigger volume, and when you divide them, you're going to end up with the same number every time. The color of an object doesn't usually change when you change the size of it. You take a piece of chalk. Take a piece of chalk. What color is it? It's green. Broke the chalk. It's a different size now. Did the color change? No, of course it didn't. It's an intensive or an intrinsic property of this chalk that it's green. It doesn't matter how big or small it is. Then there are extensive properties that do depend on the amount of substance. So I'm going to use this chalk again. When I broke this chalk, I changed its length. I changed its mass, right? Because if I have this piece versus the intact piece, the mass isn't the same. Those are extensive properties. They do depend on how much stuff there is. Intensive properties can be used to identify substances. So density is one of those that can be useful in identifying a substance. So when I was in school, we called problems like this story problems. Doesn't that sound friendlier than word problems? Oh, a story? Yay, I like stories. Story problems, how friendly. We have a lot of story problems in chemistry because this is where we take some math and we apply it to a real thing that's happening, right? So some of these problems are going to have a lot more story than others, and many times a lot of those words aren't really important. They're just kind of a setup. They're literally a story. A man receives a platinum ring from his fiancée. Well, that's nice. Is that necessary to tell us? Not actually, but it makes for a better story. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density.
As one does.
He's probably a nerd. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? So, yeah, we're going to have to look something up. What are we going to need to calculate? The density. And the clue is here, this guy is determining its density, right? It's always good to read through the whole problem and then go back and look for numbers. So the numbers that we're given here are 3.15 grams and 0.233 cubic centimeters of water. Now, this doesn't show up in the slides, but let's just talk about what that means, that it displaces water. So that's a very bad picture of a graduated cylinder. So one way to measure the volume of an irregularly shaped object, I mean, if it's a cube or a rectangular solid, you could take a ruler and measure it. But a ring, that's going to be pretty hard to calculate using geometry, right? So if we put some water in a graduated cylinder and make a note of the level in the graduated cylinder, and then we put the ring in there, what happens to the level of the water? It goes up because the water displaces, the ring displaces the water. And this difference here, the difference in the apparent volume of the water is equal to the volume of the ring. So that's how he was finding that it displaced 0.233 cubic centimeters. That's the volume of the ring. So to calculate the density, we're going to use the density equation. Density is equal to mass divided by volume. This says mass of, and then the unit gram is a mass unit, so that should also tell us, yep, this is the mass. So 3.15 grams. This doesn't say the volume is, right? If we understand what displacement is, that helps us. Also, the unit cubic centimeters is a unit of volume. So put that down here. So get out our calculators. 3 point. Yeah, and the calculator is going to be 13.519. It goes on a bunch of things. How many significant figures should that answer have? 3. So instead of writing all of those down, because I don't like doing that, I can think, I need 3 sig figs, so 5 is my last significant figure. I'm going to keep the 3, the 1, and the 5. I'm going to write down those next two, just because I think it's a good idea. And then the units, grams per cubic centimeter. Then I can round it. The next digit is a 1, so it rounds down. 13.5 grams per cubic centimeter is the density. Is it platinum? We need the density of platinum. 2 slides back. 21.4. No, not platinum. This is a 2-part story. Probably going to finish the story because you can just like this isn't platinum. The woman in this example is shocked that the ring is fake and returns it. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? Well, calculate the density again, right? Density equals mass divided by volume. 4.53 grams.
Kind of great that he was just like, yeah, this ring is fake.
Yeah. You could imagine that going all kinds of different ways, huh? Again, I'm looking at the numbers here. I'm dividing, so I'm looking at fewest number of sig figs. Each of them has 3, so I know my answer is going to have 3 sig figs. 21.367 grams per cubic centimeter, which rounds to 21.4 grams per cubic centimeter. Is this one platinum?
Yes.
Yeah. What if the density was 21.3? Should he go back and accuse his fiancée of cheating him? No, because the last digit here is uncertain. Every measurement has uncertainty. His measurements were only to 3 significant figures, so there's uncertainty in that first decimal place. So if he ends up with 21.1, 21.7, those are all relatively close to 21.4. The variation is in that uncertain digit, and so you don't let it bother you. I'll be talking to you about showing your work, and on some of the homework assignments, well, not the homework assignments because those are online, worksheets and lab reports. You show your work. This is what I mean by show your work. If you're using an equation, write out the equation, write it with the numbers plugged in, with the units, show the result with extra digits. If you want to write all of them, that's fine, but at least 2 extras. And then round it to the correct number of significant figures. If I round to the wrong number of significant figures and I have some extras up here, I can go back and fix that without redoing the calculation. If I haven't written any of this down and I've just got an answer and it's wrong, I can't figure out easily how I got the wrong answer, why I got the wrong answer, and so then I can't learn from that mistake. To get the right answer, then I have to start over completely. Okay, so showing your work is an important thing. Anybody have any questions? The density of copper decreases as the temperature increases, which is true for most things. What change happens in a sample of copper when it's warmed from room temperature to 95 degrees? Does the sample become lighter or heavier? That would be the mass changing. Does the volume, the sample expand, volume gets bigger, or sample contracts, volume gets smaller? C. Some of us can look at that and it just kind of makes sense to us, and other people are like, wait, how'd you do that? So I'm going to show you how we did that. Density is mass divided by volume. This is saying that the density is going to get smaller when the temperature goes up. We're heating up the copper. The temperature's going up, so the density has to get smaller. Does the amount of matter change with temperature? No. So the mass is going to stay the same. So we can just no, those are definitely wrong. In order for the density to get smaller, we'd be having to divide by a bigger number, right? So if V gets bigger, then this whole side gets smaller, and that's what we're looking for, and so the sample expands.